so the exercise, the last exercise of yesterday, it was, so we had the statement.
You did choose and these questions.
Okay, so we have you in liter, such that in this sense, this is 0 for any phi epsilon omega, and then for any rho, so we have this symbol means that the closure of the ball is contained in omega. So that the boundary of the ball does not touch the boundary of omega. Okay. U of x is equal to the mean value of itself on the ball. So did you try?
Yes.
Did you succeed? No? Maybe it's difficult. So the idea was to remember was to choose a test. So phi are called test functions. So the only thing that we know is the validity of this infinite family of equations, because this is an equation for any phi. So the idea is to look for a special phi for which we gain something. And the idea, of course, when you look at this expression, one thinks immediately to a phi which should have sort of radial symmetry. Okay? So radial symmetry means that either a paraboloid in this way or in this other way. Okay? One of the two, like this or like this. So we choose this phi of x equal, so we choose something like this, say. And then we want this, so this is x naught. So this is the ball, say, the radius rho. Okay. And now we want this to be 0 on the boundary of omega. So this is omega, say. And so the idea is to force this function here, to force it to be 0. So where it is negative, we pick the maximum between 0 and itself. So phi of x is, so this object is here rho square minus x minus x naught square, and this is a paraboloid at level rho square, say. And then we truncate it, so the max so this function phi actually is in Lipschitz, because here we have angles, right? I mean, this is not vertical. No, so the gradient somehow is not defined here, but still it is bounded. We don't have something vertical, we just have something. So phi is in Lipschitz. And since this ball has the closure contained in omega, this is a positive distance, and therefore phi is compact support. Okay. so let's try to see what happens to this choice of phi. So with this choice of special phi, so let me call it, okay, phi, this becomes, so maybe, okay, phi. So grad phi of x is what? It is inside, outside, outside the closure of the ball, it is clearly 0. 0, sorry, 0. Here. Inside the ball is what it is. So inside the ball is twice. Minus twice. Yes, minus twice x minus x naught inside the ball. So this function is almost everywhere defined. It is in ad infinity. That's it. So we can use it here as a test. Okay. There is no object concentrated or measure or whatever. This is an ad infinity function. I can use it here. So this integral actually is just an integral on the ball, reduces to an integral on the ball, and so we get integral on the ball of grad u of x, sorry, grad u at x, scalar product x minus x naught dx, and this must be equal to 0. And now let's try to use, as usual, the divergence theorem. Okay. So we use the divergence theorem to this vector field. So the divergence of this product is, I think that we said also this yesterday, if I'm not wrong. So this scalar product plus u of x, the divergence of the vector of the position, say. The divergence of the no? Yes. The divergence of the position vector is just n. Okay, so this is grad u of x, scalar product x minus x naught plus n, the dimension of the space, multiplied u of x. So if we integrate this over the ball, we get that this is the integral of the ball x naught and u of x. No? So that this is equal to, by the way, this is also by the divergence theorem, this becomes an integral of the boundary, and I have the scalar product of the vector field with the outward unit normal. Okay? So this is u of x, and the scalar product of x minus x naught times the outward unit normal at x on the boundary. Okay? This is outward. So this means that now this object here is just so that this object here is just this minus this. Okay. So this is equal to the integral d rho x naught ux x minus x naught scalar product out of unit normal to the ball minus n the integral on the ball. So this is a surface integral, this is a volume integral dx dx. Now let us compute the outer unit normal. This is equal So, with this observation, we get that this is just scalar product of this with this, so it's the norm squared divided by the norm. It is, yes, exactly. So this is actually rho, as you said. So this is because x is on the boundary, so the distance between x and x naught is rho. So this is equal to rho. So we find this, so this must be equal to 0, no? So now let us compute separately d over d rho of 1 over rho to the n, the integral over b rho x naught u of x dx. So let's see if we can relate, so this we know it is 0, this minus this must be 0, and now separately let us see what happens to this computation. So this is, so we have minus n, which is here. Then we have rho to the n plus 1. Okay. This is multiplied by this integral. No? Plus d over d rho this integral here. Do you have some idea on how to compute this derivative, or which could be the result of this derivative, where the dependence on rho is just on the domain of the integration, it's not...
This may be
Which could be the idea? So it's not difficult to do, but we can imagine also the result. If you, so one possibility to do this one way to see it is, so you have, so call this function h of rho. So h prime of rho, what is it? Is, say, almost. No, do not call h. Call this G. No, G. call it psi. Okay, this is almost psi prime on rho is approximately. Okay, is approximately. Yeah? So let's just do the quotient. So this is what? Is the integral over, is 1 over h, and then we have the integral over the ball of this radius minus the integral of the ball of this radius. So actually we are integrating on sort of annulus. H is small, maybe positive, maybe negative, doesn't matter. So we are integrating over this annulus. And then we have to let h to 0 in order to define what is the derivative of psi. So we are integrating on an annulus, and the width of the annulus is exactly h, or say absolute value of h. No? But I am dividing by h here. So what do you expect to be the result when you let h to 0? H is going to 0. This is rho plus h. This is rho. So what do you expect? Where do you expect to go in the limit? Huh?
0.
No,
No,
0.
this is
Because you are dividing by
If h
h.
goes to 0, so this is goes to the boundary of our ball.
Okay, fine.
Okay. Exactly. So this converges. The only reasonable solution to this. And there are no problems in defining, of course, this integral because u is smooth, so it is well defined on the surface. So it's not difficult to see actually that this, as h go to 0, it's correct, it's the correct result, okay? So I can continue here. So this is equal minus n divided by rho to the n plus 1, the integral over this ball, d over x dx, plus 1 over rho to the n, integral of the boundary of the ball, d over x dx. dx or not dh n minus 1 dx. Okay. And now this, you see, is very close to this one, because if I take this and how can I, so if I divide this object, this is 0. So it is also 0 if I divide it by rho to the n plus 1. Okay, so 0 equal 1 over rho to the n, so let me divide this by rho to the n plus 1. So this becomes 1 over rho to the n, so this becomes the integral of the boundary, u of x, dh n minus 1 of x, minus n rho to the n plus 1, divided by rho to the n plus 1, integral of the ball, u of x dx, which I hope to be exactly that one, is exactly that one. Okay, so what does it mean? It means that 0 is equal to this, but this is equal to this derivative, so this means that 0 is equal to this derivative, provided that we have this assumption that now I have erased. Okay, so 0 must be equal to this. So this means that if I define the function v so let me give this definition. For any positive rho, for any x as above, for u. So this is equal to 1 over omega n rho to the n integral over the ball of x dx. This means that the derivative of v with respect to rho is 0. So this means that v is constant with respect to rho. Okay? So for any rho, v does not vary. On the other hand, v is constant. Sorry, rho positive, small enough, rho, where is it defined? Is constant. So now I can take the limit as rho goes to 0 plus. No, I don't need it. I don't think I need it. So this constant is also this limit, right? So this is a constant. So this constant is also equal to this limit. But u is continuous at x. Maybe this is what you were saying. Okay, for a continuous function, u at x is equal to the limit of the mean value of u on a small ball shrinking to the point x. No? So I have u at the point, I take the mean value, this point is the center of the ball, I take the mean value of u on the ball, I let the ball shrink to 0, to nothing, and since u is continuous, u of x is exactly equal to the limit of the mean values. Otherwise, there is this famous theorem that this is equal almost everywhere, but here u is continuous, okay? So we don't. So this limit must be equal to u of x. So this identifies the constant. This constant k is a constant c. So this c is also equal to the limit, which is in turn equal to the value of u at the center. Okay? So we have shown that u of x is equal to this constant. So, but this constant is v. So at the end, u of x is equal to its mean value without taking the limit also. Huh?
Can you repeat it? Can you repeat that last part?
Yes.
You were saying that without the limit.
So this is a constant for any positive rho such that the ball is contained, the closure is contained in omega. So this is a constant, let me call it c. Now I take the limit of this constant as rho goes to 0, it is again c. Okay? But on the other hand, if I remember what is the definition, this is the mean value of u, so this limit converges to u at the center. Ux not, sorry. Thank you. Sorry, Ux not. Yes, yes. So, so this constant is equal to this limit, which is equal to Ux naught because u is continuous. Okay. In particular, continuous at x naught. Okay. So what we deduce? We deduce that u at x naught is equal to c, but c is equal to this. So it's very rigid. I mean, u at the center is equal to any of its mean values, even if I move rho, the mean value remains constant and is equal to the value at the center. I don't take the limit. So we get a famous formula here. So let me state it as a theorem maybe. So we have proven something slightly stronger because we just used a sort of solution in a distributional way. But so let me write it in this way. So let me write it in this way. So a corollary maybe. Let u be harmonic then for any x, this was I think VU x naught rho. Yes, this was x naught. This was x naught, no? This was x naught. Okay. Yes, this was x naught. X naught is fixed. I'm integrating with respect. So please correct this x naught here, here, and here 3 times. Okay. So then, for any x in omega, for any rho such that b rho x is contained in omega. Actually, I think that the same holds even if we just have this. So I think that we can, in any case, we have proven with this inclusion. So we have that q of x is equal to v u x rho, which is equal to omega n y. Okay. So this is called the volume mean value formula for a harmonic function. Volume mean value formula for a harmonic function. Okay? This is a famous result. I mean, it's a classical standard result. So now let's go on, maybe with some okay, let's see. So we have the volume mean value formula. Actually, the harmonic functions satisfy also some other kind of mean value formula. So let's see this theorem. Suppose that U is harmonic. So let's say x in omega, rho positive, b rho x in omega. Define another object here. Let me define it here. Is just a surface u x rho. It is mean value, but not volume, just surface mean value. So u of y, u of y, Vhn minus 1 y. Instead of taking a volume, just take the surface. I just integrate on the boundary of the ball. And then I divide it by the n minus 1 dimensional area of the boundary of the ball, which with our notation was this. Okay?
And what is V? Why is V?
No, u. This is u. Sorry, this is u. For any continuous function, you can define this object. Okay. Okay. So the theorem says that then not only we have that u of x is equal to v, but then u of x is equal to s u x rho. Okay. For an harmonic function. Let's see if we can prove it. So define f rho, so fix such an x, such a rho, etc. And define f of rho which is exactly this function here. So 1 over the sigma n minus 1 rho n minus 1 is exactly this. Boundary will be rho x, u of y is ph n minus 1 of y. So we pretend this to be constant, right? Because this is the assertion of the theorem. This is S, and this theorem is saying that this is the right-hand side is actually independent of rho. This is what the theorem is saying, right? And again, if it is independent of rho, again by continuity, since u is continuum at the center, this constant must be u at the center. So if we show that this is constant, then this as above more or less is the same conclusion, no? By continuity. So what do we do here? So the idea is to show that this is constant with respect to rho. The idea is to show that the derivative is 0. But we have to show it is differential. And it is less clear than before, because this is, before it was a derivative of a function where the function was a volume integral and the rho was only in the domain, but it was a volume integral. And so it was very easy to see which should be the result, not because we had an annulus, but we divide the annulus by the height, and the idea was that when the height goes to 0, the annulus divided by the height reduces to the core, say to the surface. So it's just no. Now this is less clear. So plane f is differentiable with respect to rho. As I said, the problem is that rho is here. If rho were inside, then there should be no problem. No? But rho is unfortunately here. So how do you see the idea for moving rho from the domain of integration to the integrand? Which could be the idea? Divergence theorem, I don't know how to use it at this level, because this is already a surface integral, so, and it is not clear what kind of normal flux it is, no? So I would know, I don't know how to use the divergence theorem here. Do you have some suggestion? This? Which could be the way to make rho disappear in that domain? No? What if we transform the integral on a fixed domain? How can we transform the integral on a fixed domain?
Unit sphere.
For instance, a unit sphere. So what do we do if we want to transform this in the integral on a unit sphere?
We define y to be equals.
So y is on the boundary of B rho, right? So if we do y divided by rho, so if let z equal y divided by rho, or which is the same, y equal rho z, then z belongs to the boundary of the Borel. Let's see what happens to the integral. y, we have seen that y is rho z. Now there is a Jacobian.
Rho n minus. Rho n minus.
Exactly, rho n minus 1. Be careful, because this is an n minus 1 dimensional integral. So it is rho n minus 1. Okay? dHn minus 1 of z. Okay? So that's not bad, because not only we have that rho disappear here, but we also have a cancellation, which is somehow natural. So we have 1 over sigma n minus 1 integral of the ball. Now the radius is fixed and rho is inside. This shows that f is differentiable. And we can compute the derivative. Integrate, so putting the derivative in under the integral sign. Okay. So f prime of rho now, I just differentiate this. 1 over sigma n minus 1. Now I don't have problem in the domain. The domain does not move with rho. No, so I can just put the derivative inside, because this was the problem. Okay. And so we find, what do we find? The gradient of u evaluated at rho z. Then I have to differentiate with respect to rho, so we keep the scalar product with z. Right? And now we could go back to the previous. So let me now go back to the, so rho z equal y. So let's see what happens if I go back to the previous coordinates. Okay. So what do I have? Actually, this is okay. So so y is in the ball. So z is in the ball of radius 1. So this is before is in the ball of radius rho. So we have this transforms in the ball of radius rho. This transforms into gradient of u at y. Z is equal to y over rho. Y over rho. Okay. Sorry, this is maybe I'm doing the computation for x equal to gradu rho z, x equal to the origin for simplicity, maybe, because I would like to have the normal at some moment. So so we can do this kind of computation. So yes, because this should be, so could be y minus the center. So let's take x equal to the origin, because there is nothing changes. So for simplicity, let's take here x equals 0. Otherwise I have to rescale. So this is 0. This is okay, this is 0. This is 0. The same is okay, so this is 0. This is 0. Yeah. No. Now dHn minus 1z is 1 over rho to the n minus 1. dH minus 1 of y. Okay, so this is nothing but, you see, now it is y minus 0, so it is just y on the boundary, which is the position vector, divided by its norm. So it's exactly the outward unit normal. Okay, so this is equal to 1 over sigma n minus 1 rho to the n minus 1 below 0 scalar product of what we have denoted by the outer unit normal at y h n minus 1. So this is a normal flux. So exactly is this integral here is just the integral of the Laplacian of u, no?
Yes.
Because this normal flux, you see, is the normal derivative of u. So if I integrate the divergence of the gradient, which is the Laplacian, it is exactly this quantity. So this is actually the volume integral of the Laplacian of u, which is by assumption is 0 because it is harmonic. Okay. So this is equal 0. And so this concludes the remark that for a classical harmonic function, I mean for a harmonic function, classical or not, is C2. So
Sorry. Is the divergence by the divergence theorem? That's what makes the integral of the Laplacians of u.
when you write the divergence of the gradient of u, the divergence of the gradient is by definition the Laplacian. Okay. But this is also by the divergence theorem is the grad u scalar the unit, the outer unit normal, which is what it is written here. So this is the Laplacian. And which is 0. So this we have shown that small f is differentiable for rho positive. We have shown that f prime is 0. Therefore f is constant. So it coincides with the limit at 0. The limit at 0 is q at the center because u is continuous, and we end up with the conclusion. Okay? So this is the proof. So let's see, I want now to improve a little bit this, and let's see what happens if we suppose that u is subharmonic, you know. Okay? Let's see what happens to this proof. Instead of knowing that minus is a classical subharmonic, not a variational subharmonic, is a classical subharmonic. Okay? So let's see what happens if we can improve a little bit this proof. So we keep the same f. So f is differentiable for the same reason as before. Nothing changes. F prime is this. Where are we using?
In the last part.
In the last part.
To be greater than 0.
But here we have to be careful about the signs.
To be greater than 0.
Yes, exactly, because this actually turns out to be, if I am not making mistakes with the sign, Laplace of u x, right?
Yes.
Now, subharmonic, classical subharmonic, meaning minus Laplace of u less than or equal than 0. Hmm? So, which means Laplace of u larger or equal than 0. So what do we have?
So derivative is larger than 0.
Larger than or equal to 0.
Is increasing.
So f is non-decreasing,
Nothing.
right? So f is non-decreasing. Well, if it is non-decreasing, f is non-decreasing, so it admits a limit as rho goes to 0 plus, which is u of x, but it is always non-decreasing. So u of x, which is the value at rho equals 0 plus, is less than or equal than the value of f at any positive rho, because this is non-decreasing, right? So there is the interesting conclusion here, then u is below, not above, see? It's the surface mean value. So the previous theorem was called the surface mean value formula, the previous theorem, sorry. So please add to your notes. The previous theorem, the theorem with the equality and harmonic with the equality is called surface mean value formula. Now we have a little bit to generalize it, no? And we have shown that for a classical subharmonic function, we have, say, a surface mean value inequality with the less than or equal to. Okay? And for superharmonic, we have that u of x is larger than or equal to. For superharmonic, okay? Because it is enough to change u into minus u, okay? So, by the way, this gives a third way to define what is a subharmonic function in a weak sense. Morally, is more or less, one possible definition would be, apart from lower semi-continuity, subharmonic for upper semi-continuity, okay, but one could say that a function is, say, morally, if you want a continuous function, say, is morally subharmonic, is subharmonic, if we have this, for any x in omega, for any rho satisfying this. I need continuity because I want to speak about a surface integral, so if u is not continuous, I don't know how to define a surface integral of a discontinuous function. It does not leave any trace on a surface. Is this clear? If u jumps, there is no clear value of u on a thin set, on a surface. So I need continuity. So, also this condition now, I cannot improve it into just this symbol, because suppose that omega is a ball itself, so u is defined inside, but I'm saying nothing about its value on the boundary, so I cannot take omega, the ball equal to omega itself, because on the boundary of the ball, this is not defined. So I have to be slightly inside. Here I can do, but up to the boundary you cannot. Okay.
Upper semi-continuity is enough to define.
Yes. upper semi-continuity is enough to define a surface mean value formula, because upper semi-continuity is actually a concept which is pointwise defined everywhere. So you say that a function is upper semi-continuous at any point if u of x is larger or equal than the lim sup y converges to x, y in omega, u of y. But this is a concept defined for any x. It's not almost everywhere. So as soon as you have some sort of lower semi-continuity or upper semi-continuity, as soon as you are using functions pointwise defined everywhere, then, I mean, if they are pointwise defined everywhere, this maybe is not converging, this integral, I don't know, but in principle it is defined. If instead you have a function in L1, this is defined almost everywhere with respect to Lebesgue, and Lebesgue doesn't see the surfaces, and so this is not defined. Is this clear or not? Maybe it is not clear. We are not convinced. So suppose that you have a function which is defined only almost everywhere. In the plane, say, in the plane. So, and now you have a surface in the plane which is just a curve. Okay? This curve. If u is defined only almost everywhere, here you can never say what is the value of u at this point. Because this has zero measure. So and so what does it mean integrating on a set of zero measures u itself? You can modify u in its equivalence class. There is no way to give a meaning. If you are in more regular spaces such as Sobolev or slightly more regular spaces, then you have a notion of trace on boundaries. But for LP functions, you don't have any kind of trace on a surface. You cannot speak about the value of u at a point or on a one-dimensional set. You can speak only about the value of u at almost every point. And this is a zero measure, the Lebesgue measure. Okay. So surface mean value formula. There is another way to recover the surface mean value formula. So maybe, since these are peculiar, special properties of harmonic or subharmonic functions. So for the Laplacian, we cannot. Yesterday we saw something more general because we had an integrand which was just smooth, strictly convex, and for which we were able to prove the comparison principle. Okay. What we are saying today instead is special for the Laplacian, which is the Dirichlet, corresponding to the Dirichlet integral. Okay. So this kind of probably maybe this is not this kind of formula for harmonic functions. This kind of surface mean value formula maybe is not so surprising if you think in 2 dimensions to holomorphic functions. No? It's not the same formula, right? But so because we have exactly a disk, the boundary of the disk, and we say that u, the center, is exactly equal to the u of the boundary. It's not the same. But for holomorphic functions in 2 dimensions, there is a Cauchy form, which is somehow, in some sense, related to this, because it says that if you have f at z, then this is equal to an integral of f itself divided by a kernel, divided by z minus zeta, on any loop containing z inside, right? So there is some parallel between the two. That is in 2 dimensions. So other ways, alternative ways, alternative proofs of a surface mean value formula for harmonic function. Surface mean value formulas. I'm stressing this because these formulas are so important. Okay, they are just for harmonic functions and Dirichlet integral, but they are so important that maybe it's better to see more than one proof. Okay, just to alternative proofs of surface mean value. So let me remember what we have done up to now. We have proven a volume mean value formula for harmonic function, mean value formula. Just using the idea for harmonic in a weak sense, actually, just using the idea of a paraboloid. Okay. Then we have shown a surface mean value formula, just computing the derivative of S with respect to rho, showing that this derivative is 0. Okay. Then we have done a surface mean value inequality for, say, for subharmonic functions, just showing that we have this larger inequality. So this is what we've done today. Okay. Now let's see another alternative proof of this point here. Because I want to use a representation result which was an exercise that I gave it to you. And now maybe we can. So if you have U in C2 omega intersection, I don't remember, as I stated, maybe C1 omega bar. So I think that we have some sort of, now I will make some mistake surely on the signs. So we have U dgx over d nu minus gx du over d nu. And now here there is some sign which I'm pretty sure will make a mistake. Okay. So you check please this. So where gx is the fundamental solution, so gx of y is some constant did you find is this written correctly? Huh?
dy instead of dx.
Sorry, thank you. This is a mistake. X is here. Thank you. This is y. This is y. Okay. Is this the signs are correct? I hope.
Yes.
Okay. And this was obtained just using again the Gauss-Green theorem. And take it. Do you remember? So the idea was to work with this object here, right? And not on the wall of omega, because we are taking a singular, one of the two v say is singular at x. So in order to apply correctly the Gauss-Green theorem, we remove a small ball. So we work on this, and then we are able to pass to the limit, this integrating by parts, working a little bit, passing to the limit as rho goes to 0. We end up with this formula. Okay. I left this as an exercise, but the idea of the exercise was exactly the same when we proved that. Okay, it was the same proof of this. No, well, I think that we made this for x equal the origin. No? Do you remember? We made this exercise. We made this exercise for x equal the origin, but if we translate it for any x, clearly we also have this in the sense of distribution. Okay. So the same idea that we used to prove this exercise leads to the formula, but I think that I told you the details, no? Enough details, so I don't have to repeat it. No? Okay. So I don't repeat it. Okay. So let's see what happens here. So now we have a ball. We have a ball. And we have a function which is harmonic in the wall of omega. So the ball has closure contained in omega. So U is so now we can do this on the ball. Say. And U is harmonic, therefore this is 0. Okay. Now we have to compute a little bit something. One is not terribly difficult, because let's see what happens to the second addendum. So we have the integral on the boundary of B rho x of gx. Again, we could fix x equal to the origin, just for simplicity. Okay, let's do this for x equal to 0 for simplicity. I think that when x is equal to 0, this was just denoted by g without x. Okay, it's not g0, it's just g. G. Okay, so du over du 0. And if x is 0, so let me omit the parentheses, so just be. And so this is now g. Suppose that we are in larger or equal than 3 dimension, otherwise there is a logarithm. So let me work for n larger or equal than 3. So g we know is a constant divided by rho to the n minus 2. 2. Okay, in 3 dimensions it is the Newtonian potential. So 1 over rho, n minus 2. Yes. Now there is some constant. And so what do we get? We get just du over du, 0. And again, this is a normal flux, so it is equal to the integral of the Laplacian, which is 0. Do you agree? Mm-hmm. Same computation. So this term here does not contribute to the final computation. Is it okay? Mm-hmm. This integral is exactly the integral, this is the outer normal, it's just the integral of the Laplacian. The volume integral of the Laplacian. 0. Fine, so actually u of x is nothing but just this one. And the hope is now that this should be the formula that we want. So u is here. So this is somehow reasonable now, because we are integrating on the boundary of the ball. U at the center is integral on the boundary of the ball. U is here. G is radial. It goes like 1 over rho to the minus 2, n minus 2. So its derivative should go like to the 1 over rho to the n minus 1, which is of the order of the surface area of this. So this, hopefully, no? Have you followed the reasoning? So let's look at this formula. Now we do the computations, okay? But just look at this formula here. U at 0, the center, is equal to integral on the boundary of the ball, U itself. That's okay. But there is this. But remember, the G is radial. And it goes like 1 over rho to the n minus 2. So maybe this derivative could go to 1 to the rho, like 1 to the rho to the n minus 1. Hope. If it is so, this is like the order of this, because this is n minus 1 dimensional. So this seems to be a sort of mean value. Let's see. Okay, so G of, so this is G of y, see, is equal to some constant that was, to be precise, I think it was sigma n minus 1, n minus 2, 1 over y, n minus 2. Huh? Right? So the gradient of G of y is the same constant, sigma n minus 1, n minus 2, then we have 2 minus n here, then we have y over y, and then we have 1 n minus 1. Okay. Correct? Check it. Please check if you agree, otherwise we discuss.
Yes.
It's okay. So now, so there is a cancellation here up to a sign, which is not bad because here there is a minus. So my hope is to kill this minus. Okay, so it's minus 1 over sigma n minus 1, and then we have 1 over y n minus 1. And I think that we are almost done because this is the normal. The normal derivative is just this gradient scalar product with the normal itself, the unit normal. The normal itself is this. So there, at y, it means that it is exactly this. So this counts, I mean, this is scalar product with this is just 1, so this is equal to minus 1 over sigma n minus 1, 1 over y n minus 1. As you see, and you see, it is happening exactly what we expect. Because this now there is a minus, and the minus builds, so we have 1 over sigma n minus 1. Then we have 1 to the rho with the correct power. And then what remains here is just u. But this is the n minus 1 dimensional area of this, so this is the mean value, so this is S. S of u and 0. So this is second proof. I prefer the first one because it's more direct. I don't use this. Sorry, I don't use the theorem I erased. I don't use the theorem u Laplace of v minus v Laplace of u. This long expression. I just differentiated S. So it's very easy. Once you show it is differentiable, you compute the derivative and you show it is 0. That's it. So for me, that proof is more direct. But this is another standard proof that you could give. Okay. And this proof is so direct that immediately gives also the generalization to subharmonic. Okay. So this is another proof, and then I would like to reprove also the volume in value formula. Now, this was difficult because that was based on a strange, clever choice of test, which is something that it's usually difficult in PDEs to. Only very strong mathematicians are able to produce the correct choice of sub-solution or solution test or whatever in order to make things right. So alternative proof for harmonic functions. So let us start with the volume V, with the mean value V at x rho. So this is by definition is the mean value, is the volume mean value. So let us write it what it is. Omega n rho to the n integral b rho x u y. And now we can split this volume integral by levels, looking at integrals on the strata invading all the ball. So the formula is sort of Fubini-Tonelli section formula. Is just integral from 0 to rho, integral on the boundary of Bs x, the integral itself does not change, no, Bs. This is an important formula which essentially says that if you want to compute this volume, you can sum all the areas of this boundary of the disk, fourierating from 0 to rho, all the...
Okay, so in the integral it should be the bonus of radius S.
The boundary, yes, sorry, thank you. Thank you. So, this is a section formula which is extremely important. Maybe you have not seen it, but let's keep as it is. Now, why I'm using this formula? Because by assumption now we know that U is harmonic, therefore we have given two proofs that U satisfies these two proofs, right? And so this means that this, what is this? Well, this must be equal to U at the center multiplied by sigma n minus the surface area of the boundary of the ball of radius S. Okay, so by the surface mean value formula, that we know it's true, this must be equal to sigma n minus 1 S to the n minus 1 U at the center. Okay. So let's substitute and see what happens. So we get now U at x, of course, is independent of S, so it goes outside everything. Okay. So this and now let me rewrite this 1 over omega n rho to the n. U of x is outside. The first integral remains from 0 to rho. 0 to rho. Sigma n minus 1 goes outside. Okay. And then we have S to the n minus 1 ds. But this we can do explicitly in the integral. So which is 1 over n rho to the n. Okay? So sigma n minus 1 omega n rho to the n u of x times 1 over n rho to the n, right? So let's do some cancellation, rho to the n and rho to the n. And remember, one of the exercises that we did, I think that we did this interesting relation between safe surfaces and volumes. You remember we did this maybe in 2 different ways also. So this means that we have a cancellation, a very precise cancellation. This remains u of x. Okay. And so we have also the volume in value formula. So we have also another way to prove it. And notice finally, is this clear?
Yes.
Okay. Notice finally that if we have surface mean value inequality, instead of having the equality, we just have the less than or equal than, then here we keep exactly the same inequality. So this shows that a subharmonic, classical subharmonic function not only satisfy the surface mean value inequality, so that u of x is less than or equal than its surface mean value, but also u of x is less than or equal of its volume mean value. So we have shown finally also as a consequence that if u say is C2 subharmonic, then for any x in an omega rho, etc., as above, we have this. Okay, so this is the sort of situation concerning the volume mean value formulas and the surface mean value formulas. How to remember? For subharmonic, we have less than or equal. For super, we have larger than or equal. For sub, we have, and it's important to remember to put a minus, otherwise we make a terrible confusion. So this one has to fix once for all its own choice of the signs. Okay, I prefer to use the minus exactly because for me it's easier to associate the word sub to associate with less than or equal. Okay. Fine. So now let me go back to this kind of. So what we have seen yesterday, and now you are telling me that it has not been, there is no registration of yesterday's lecture?
Yeah, they've not uploaded it. Maybe.
But did you ask to the...
No,
You
I
should.
should ask them. I just check on the YouTube just to...
Okay. Strange, eh? Because
Sometimes it takes time.
it takes time.
Sometimes.
Ah,
So
it
you
takes-
should wait till like tomorrow, maybe it will get booked.
Let me know if it doesn't appear because it's. So yesterday we saw comparison principle. You remember yesterday what we saw yesterday? We saw that if U and V are two Lipschitz omega say bounded open set. Bounded open set in array. U and V are Lipschitz. Okay. U is a variational subsolution. Variational subsolution, I call it. Variational subsolution. Variational subsolution of capital F. And capital F was not any, but it was an integral of a strictly convex smooth integrand, even also, for simplicity. So F of U was integral of U F say C2 F of psi is equal to F of positive say and strictly convex. A typical example, the lecture of today is the Dirichlet. So yesterday we saw that if U is a variational subsolution of F, if V is a variational super solution, variational super solution of F at the boundary U less than or equal than V, then U less than or equal than V inside. So this is a variational wake comparison principle, so we can compare if we have that the two objects are one below the other on the boundary, that this remains the same. And we made several comments on the consequence of this. Remember, supremo U minus V, etc. Okay. So now we want to see sort of similar result. And the advantage of this was, one of the advantages was, of course, this generality, but also we were not using the operator. We have never written yesterday, in the proof of this, yesterday we didn't write minus Laplacian, or the first variation of this, never written. Just only the energy, just only the argument was based on the integral, not on the PDE, but just on the variational point of view. Okay, you remember the proof? It was sort of not terribly difficult. Okay, now we want to look at this, but from the classical point of view. Okay. So let me at least state following theorem. So, which is very related to this. So let omega be bounded open set. Be bounded open. Suppose that U is be subharmonic. Oh, subharmonic, well, we have made some example in the first lecture, but morally it's not true. It's related to convexity, right? Mm-hmm. So in one dimension. Okay. This. What is special feature of this? So it is suppose it is not constant. Okay. So it's something like this. Okay. So what is the feature of such a function? You have a domain, omega, and you see this object here. Where are the maximum? The maximum point of this object on the boundary. Okay. So of course we cannot exclude that this function is constant because. So if it is constant, all points are maximum point, both on the boundary and inside. So if I want to give some statement concerning the maximum on the boundary, I have to be careful that I don't want to exclude interior maximum, because these are all interior maximum points. Okay? But what I can write, probably without making mistakes, is something like this. Supremum of u on omega equal what?
Boundary.
Supremum, do you agree? Supremum of u on the boundary of omega. Do you agree? So now you see, I am supposing that omega is bounded and u is continuous up to the boundary. Okay? So this means that this, actually u is defined also on the boundary, and this is a maximum. Okay? And also, this supremum on omega can be seen as a maximum of u on what? Where?
Closure.
Closure, no? Because think about this example. The supremum of u is not a maximum. Supremum of u in omega is not a maximum in omega, but is a maximum in omega bar. So another way, supremum of u in omega is equal to the maximum in omega bar because u is continuous up to the boundary, by the way. So this is max of u in omega bar. Okay, so this is, if you can write one of the values, one version is this. Okay? One version is this. Also this one is okay because they are all equal. So
Is this maximum principle for superharmonic functions?
this is so-called weak maximum principle for classical subharmonic functions. Weak, no, you're right, so it's better to be precise. This is called the weak maximum principle for classical subharmonic functions. Of course, if you have a superharmonic function, then you have a weak minimum principle. No? So you have simply to change u into minus u. Okay? Our operator, everything is even here. So if you change u into minus u, then remember that you get the weak minimum principle for classical superharmonic functions. Okay? This is what you get. Okay, I think that today, time is over. So tomorrow we will prove this, but maybe you can do. Let me give you an exercise for tomorrow. Supposing this is true, take this for granted. Prove the comparison principle from this. So exercise. Suppose that theorem 1 is true. So let u and v, so let omega bounded, okay? Open, bounded. Let u, v, c2. So let be classical, subharmonic, respectively superharmonic. Okay. Suppose that u is less than or equal than v on the boundary. then the same remains true inside. So this is a comparison principle. Okay? Yeah?
U minus B is U minus B superharmonic.
Yes, but prove it. It's immediate, I agree. But in omega, yeah, I agree, it's immediate, but maybe why don't you write it? So this shows that from the weak maximum principle, we get the weak comparison principle. Yesterday, we showed the opposite. That we proved yesterday the weak variational comparison, and from that we deduced this.
Yeah.
So just yes, another way to say the same. So this is an exercise for tomorrow. Just a last comment before I don't have time. I want to comment on the proofs, and it takes. Maybe so, but just one comment that a boundedness of the domain is relevant here. So, example, let omega be the half plane in R2, so let m equal 2, and omega be the set of xy in R2, such that y is equal to 0. Okay, sorry. Y is larger than 0. Okay, so the positive half plane. And take u of xy equal x. Okay. Then u is harmonic, so in particular it is surely subharmonic. Polynomial, linear polynomial, so therefore surely it is harmonic and therefore it is subharmonic. It is C2, of course. And u is 0 on the boundary of omega. Right?
Yes.
That's what X is
What-
The upper plane.
No, not the other plane. Maybe take y here. Y. Okay. The boundary of omega is y equal to 0.
is Y equals to 0.
Okay. So, and u is equal to y, u equals 0 on the orbital. But the supremum of u is, of course, different from 0 in omega. The supremum of u is plus infinity. So, in the theorem 1 is false. The supremum is not 0 in omega. The supremum is. Now, the omega is unbounded, so the supremum is a supremum and is not necessarily a maximum. But it's clear that the supremum is plus infinity.